Hello, everybody. I'd like to welcome you to the Critical Materials Innovation Hub webinar series. And this is a series that's done for and by CMI. And I'd like to tell you a little bit about this webinar. First off, these webinars are hosted by Colorado School of Mines. And if you have a suggestion for a future webinar, we're always anxious to find something that will serve you. So please put it in the exit survey or email us at cmi@mines.edu. This is a public webinar, and a recording is going to be available next week at aimslab.gov/CMI under the webinar menu and on YouTube as well. So don't hesitate to get on that YouTube channel. Questions, we're going to hold those questions to the end so that we can answer them and make sure that you have all of the questions, we have all the questions answered. But so that will be following the presentation. However, as soon as you have a question, if you would put it into the queue, that would be wonderful. So I'd like to introduce our presenter today. So Dr. Ku is the co-founder of Xiron Global, a strategic advisory group serving clients in the areas of clean energy, materials, and sustainability. He's been active in materials sustainability, including work with GE, also chairing an industrial advisory board for the EU's International Roundtable, and also serving on CMI's Industrial Advisory Board. He has a PhD from Princeton University and also MS and BS degrees from MIT, all in chemical engineering. And I don't want to take any more of Dr. Ku's time, so Anthony, if you wouldn't mind taking it over from here.
Yeah, great. Thank you, Cynthia, for the invitation to be part of this. I was looking at people as the seminar or webinar was getting started, so it's good to see some old friends as well as how the community's grown over time. So at the beginning of 2023, I was in a group of people. We were talking about, what are the existing challenges related to understanding what materials are critical, what's understood, and what are the real outstanding problems. And what that led to was a conversation and then ultimately a paper, a perspective paper that we ended up publishing in Joule earlier this year. And that's the foundation for the presentation that I have today. I'm going to run through, as you can see, the topics on the right side of the screen. First, an example that hopefully will be useful, and then talk through the challenges. And the idea is not to go through all the details of the paper, but to pull out some of the highlights, and then also to elaborate on that with some personal observations and anecdotes, which hopefully will be a useful use of your time today. So as a motivating example, I know rare earths is something that the CMI is very, very interested in, but I'd like to turn the clock back about 35 years to 1989. And this is actually a report that was put out by the USGS mapping out where are the different operations that exist in the world for both mining on the left and then refining on the right. And you can see some of the usual suspects, mountain passes here in the US. Australia was pretty active. Brazil had some mining sites. And then on the refining side, there was a fairly significant footprint in the US. Japan was a big player. And then there were also starting some different sites in China were being developed. But if you look at it by the numbers, you can actually see in the upper right-hand corner here, the production actually was, the production costs actually were quite low, but at the same time fairly distributed, suggesting different places in the world where we're still figuring out how to make these production chains work. If I move forward to the next page, I can actually overlay the actual levels of production. And at the time, the US was still one of the largest producers of rare earth oxide components, along with South Africa, in terms of potential. But in terms of China, in its role, where it stands today, is a very dominant position. But back then, it was still, relatively new on the scene. Deng Xiaoping in 1987 had mentioned this fairly famous quote that the Middle East has oil and China has rare earths, signaling this intention to try to establish a strategic presence in rare earths. And so this is 35 years ago, where if you look at this processing map, what I've highlighted here is where the most significant processing capabilities were occurring. So even though there were processing sites in China, most of the rare earth separations were occurring in Japan, in France, and then in the US. If we now turn the clock forward to today, this journey then leads us to the point where China occupies a dominant place in the rare earth supply chain, from production, if you look on the right, but also downstream into refining and then integration into actual products such as rare earth magnets. If I track the actual volumes of production, you can see again this initial signal by Deng Xiaoping to improve China's position in the rare earth supply chain gave way to growth. There was the first rare earth crisis, at least the one that I was able to participate in my career in the 2010s, where basically there was an incident between China and Japan that led to an embargo of rare earths. It triggered a variety of actions globally. And then in the current frame, there's also a renewed interest in rare earths and the challenge there. So I use this historical perspective to highlight what we think are really three important dynamics or issues that are worth looking at. The first is it's not just about rare earth or any critical material production. The actual full supply chain matters because risk can show up anywhere. So that's a theme I'll unpack as challenge number one. The second is that things change over time. So a snapshot taken in 1987 or 1989, 2008 versus today will show you some very interesting things that can be done, but those things can change on you. So challenge number two will be to think about how do you begin to understand dynamics better and what that means in terms of identifying risk, but more importantly, managing risk. And then the third piece is this idea of what's generally considered an exogenous factor in a lot of the modeling results, geopolitics or other political factors, these things that are not necessarily driven by technical factors, but really do end up shifting a lot of the dynamics of what's actually happening. And so how do you think through ways to begin to capture those exposures and the uncertainties with that? Those are the three issues that came out of the conversation that I had starting in 2023. And I'd like to use some time today to unpack those for this group and see if it's useful in terms of thinking through how can we better understand where the risks are and what we can do about them in critical materials. Just to calibrate everybody, I think most people on this call understand what critical assessments are, but just to remind those or introduce this to those that aren't, the idea is something that is considered critical based on two factors. One is if there's a chance that you could end up with a disrupted supply. So that's, imagine a supply risk axis where something is hard to come by. There's a higher risk of it. And then if there is a disruption, how bad is that for you? And that's the other axis. And so things in the upper right-hand corner where there's a high chance that you could lose your supply and it's very impactful are things that would be considered critical. And if it's lower on either of these axes, there's less of a concern. So what I have on this chart are plots from the US Department of Energy. This is their most recent report from 2023. There are also ones from around 2010 that show a similar type of frame. But in this case, you see different materials that the US Department of Energy considers at risk and also impactful when you think about clean energy technologies. Back when I was working at GE on this problem about a little over 15 years ago, we did an internal assessment as a company level to understand if the company's unable to get certain materials, how does that affect the different product lines and the ability of the business to execute and be effective. So you have different materials that are there, but they're, again, things that end up in the upper right-hand corner. And similarly, the EU over time has also tracked this. And what I'm showing you here is an overlay of a couple different plots from 2 different years. And what you find is the different materials, a lot of them are the same, but they actually move around on the chart over time as you see production change, as you see end use change, as you see policy change. So this general idea of criticality assessments is all about understanding risk. How does supply risk actually matter? Where is it? What's its magnitude? How does it change? Identifying the things that sit in the upper right-hand corner, and then thinking, how do I move these things over to the left and down, either by reducing their significance through substitutions or other factors, or reducing their supply risk through a whole suite of actions that can be taken. So the idea here is to continue to work through this framework and this lens, but to think about how do I get better at understanding where the supply risk is in terms of the whole spectrum of real world events that we find ourselves in now as well as in the future. So challenge number one is thinking downstream of not just at the primary point of production in elemental levels, but actually all the way through the supply chain. So if I take a look at this chart on the left, what I've done is overlaid the different lists of critical materials at the elemental level that have been identified by the US government, by other governments, and even by companies and other entities that are not governments. And you find, a lot of things on the periodic table end up on that list. But at the same time, these pure elements are a starting point. It's important to go after these things and to think about that. And I know CMI has a lot of activities working at the early stages of the supply chain and further down. But to illustrate the example of why you should care about things further down the value chain, consider the case of batteries. Batteries are used as end use cases in electric vehicles, energy storage, and a variety of other applications. But when I look at a battery itself, there's a variety of battery chemistries. And so this chart you see here on the right comes from the IEA, a report on supply chains for batteries. And depending on the specific type of battery, an LFP versus an NCA battery, you'll use different types of materials in different degrees of quality and in state. So if I'm thinking about connecting supply risk for, let's say, EVs, and the fact that I might expect electric vehicle adoption to go in a certain direction, the specific type of battery actually creates this noise factor if you try to link it all the way back to the primary elements. And that's not bad, that's just reality. But then how do you connect the dots with the material that, for example, if you say there's an expectation of significant adoption of EVs, batteries are needed for those. And so lithium, for example, might be important, cobalt might be important, but then you see a pivot somewhere where the technology shifts from, let's say, an NCA to an LFP battery set, and cobalt suddenly becomes less important. Those are types of questions that are important questions that we've seen evidence of in the past couple of years, of things that really will inform efforts to think more deeply about critical materials risks and how to prioritize mitigation effects. So why does it matter? Clear understanding of risk is important. It's important not just to track mass flows, but also value flows. And then the other thing about this is if you think about markets, market competition actually incentivizes people in the supply chain to try to increase their concentration risk, right? Their market share, their ability to protect their ability to make money is something that actually works counter to what you might want in sort of an ecosystem level of managing that risk. And tracking risk downstream and materials flows downstream is hard because materials change. An element is fairly easy to identify, but if I start thinking about different grades of material, I then now start to have more entries in my spreadsheet, and I have a variety of other issues that really causes complexity to grow exponentially. And the hard part ultimately is that the data quality and access is hard. It's not just the data doesn't exist. The data may actually exist, but it might be segmented behind the firewalls of individual companies in the supply chain that will keep that information as proprietary and then make it difficult to actually get a full holistic picture of what's going on. So risk can kind of sit in blind alleys where if you had sort of the God's eye view of everything, you could pick those things out. But if you've got individual companies that understand different parts of the supply chain but aren't necessarily communicating that information, you can see emergent risks that can take people by surprise. So if I think about who actually does this well, one example might be the military. In my personal experience, interacting with folks in Department of Defense, they're very, very thoughtful about understanding their materials and supply chains needs. So for example, if there's a weapon system, there is the ability to actually go back in procurements and understand these chains and to map that. Similarly, large corporate players that have fairly well-developed supply chain functions. So when I worked at GE, that was an example. Apple, in my experience, watching their operations as a private citizen, has also a very clear understanding of these things. So it is possible to begin to aggregate data and to understand those things. But the level of individual companies that might be smaller or have less leverage or less capacity within the supply chain, that remains a hard problem. And so it's one that I'd like to flag for the community as something that requires attention. So what can you do about this? Well, there's a couple things in the paper. I'm not going to go through all of these, but what I did want to do is to get at this one example of substitutability. This idea of, well, if something's hard to come by, maybe I can just use a different element and see if I can find something to mitigate my supply risk. So the example I'd like to show you here is one that I don't think it's been talked about too much, but I think it's an interesting one. So imagine, in this case, a jet engine that has a component, a ceramic matrix composite. So in the hot gas path, replacing the metal with a ceramic component helps you get to higher temperature, it reduces weight. So there's a lot of reasons why you would want to do something like that. In order for that ceramic component to survive the hot gas chemistry, you need to put an environmental barrier coating on that, an EBC, which prevents reaction of oxygen with the ceramic to cause it to degrade. And so when you think about, in this case, I was looking at a project, and this is actually something that was published in the public domain, is rare earth silicates are actually turn out to be a pretty interesting candidate for environmental barrier coatings, that they're fairly unreactive at high temperatures. So if you coat a ceramic with them, it can protect that ceramic. So if you think about a supply chain, well, I need to go find these rare earths in order to be able to build these coatings and have some effect. The challenge comes in if you now dig a step deeper into the chemistry, that if I think about rare earth silicates and disilicates in this case, I have here in this middle chart a phase diagram where I'm plotting temperature against the different types of rare earth silicates that are there. And what I want you to notice is that there are different regions where you have crystallographic phases. So a gamma phase, a beta phase, and a delta phase. And so the interesting thing is that as you cycle this component through temperature, what you don't want to have happen is this transition through different phases, because that causes mechanical stress on the component, and ultimately the coating can tear itself apart. So the bottom line for this coating is you wanted to find rare earth silicates that actually ended up with some of the heaviest of the rare earth elements, because you were in this beta phase where you can go through the thermal cycling without the coating tearing itself apart. So therein was the challenge. The science said, go find these lutetium, ytterbium, thulium rare silicates, and let's go build these and put these on the components and see what happens. If you look at the bottom here, you can actually see, here's the 13 rare earth elements, and the separation process, actually, you start from left to right, and typically you'll pull off the lights first, and then you end up at the back end. That's where you get to the heavy. So the abundance is low, the supply chain is complicated. And so the question is, which of these rare earth silicates do you actually want to use? Do you want to do a lithium, ytterbium, a thulium? And you can go by the abundance, and you can actually switch between them, because as long as you're in the right phase region, you should be able to make it work. Well, it turns out you actually don't have to go that far. One of the things we found is the thing that matters is that if what you care about is being in the beta phase, you don't actually need a pure rare silicate, a ytterbium or lutetium. You can actually use an unseparated tailings that has an average atomic radius that's in this space. So you actually can use a lower grade material to accomplish what you need to do. And so in this case, the substitution question actually is not so much about the pure rare earth elements, but actually about the actual functional technical demand that was there. So it's an interesting example that has a lot of technical detail. I hope I didn't bore you with it, but it is one that shows there's a lot of nuance and a lot of capacity to get into the technical details to begin to understand how to really relieve supply chain pressure in different ways. So the second topic I'd like to unpack is this idea of dynamics. And dynamics is relatively straightforward from an intuitive perspective, that things change over time. And so you can end up having a snapshot of something and understanding something today, but you might not understand what it will be tomorrow or 5 years down the road. And the reason that's important is because if you think about mitigation actions, if I'm developing a technology such as is being done at the CMI, if it takes me 3 years to develop a material, and then it takes me another 2 or 3 years to qualify it, and another 2 or 3 years to get into production, but the market changes faster than that, I can end up missing the window, and that can cause some challenges in terms of the mitigation. So again, a practical example of that, back in 2010-ish, there was a move in the lighting industry from compact fluorescent light bulbs to LEDs. So this idea of the phosphors that were red, green, and blue were heavily driven by rare earth elements, so yttrium, europium, and terbium. But at the same time, this new technology around LEDs ended up changing the game fundamentally through two reasons. One is you actually needed less phosphor per unit of light generated. And the second is that the actual amount of rare earths in those specific phosphors for LEDs was also reduced. So you can see a table here that has some of those details. But you don't need an Excel sheet to actually do this. The first time we did this calculation was actually on the back of an envelope, literally, where you're now looking at a times 10 to times 100 reduction in the amount of rare earths that were needed in the lighting industry as it began to shift from fluorescent bulbs to LEDs. You can actually go look at projections of LEDs and fluorescent bulb market share. And that's what you see here, is just working through the simple math of how much rare earths would you need if you just take certain projections from the US government, the DOE in this case, as to the different shares of lighting technologies. And then the first derivative of that is at the bottom. It says you actually have this interesting inflection point in 2019. So if you turn the clock back to around 2010, which is when we were thinking about this question of, rare earths, there was a crisis because of the Chinese, Japanese issue, and then that followed on into the US. Would there be enough rare earths? Should we be investing in mines? What should we be doing? Well, one of the things that we noted at the time was if LEDs really were going to take off, and there was a strong economic case for that, you could actually see at least some of the pressure on yttrium, europium, and terbium start to decrease within the next couple of years, independent of anything you did with respect to supply and other things. And the interesting piece about that is we look at the value of these particular rare earths in the overall stack. They actually really drove the economics of some of the mining projects. So this insight led us to think hard about, whether as a company it made sense to invest in further mines and supply and other things, versus allowing this natural market evolution, this technology inflection point, to begin to relieve some pressure. So again, just to illustrate the dynamics are easy to describe at a high abstract level, but to try to illustrate that with a specific example of where it actually did happen, that the market was changed by a non obvious inflection point. In terms of promising directions, what can you do to understand these things? Well, there's a couple places you can go. One is there's great work being done at the USGS, in the EU, and in other places of creating dynamic dashboards. So you can take these snapshots of critical materials assessments, and you can begin to connect them to live data sets. And so you can begin to see how these different elements can begin to change over time based on the data that's available. So that's a great step forward. I think personally, there's a great opportunity for research into understanding the different cycles and the time constants at which the different components of risk can change. And so what you see on this graph is just a cartoon that shows the different life cycles that you can have: a short cycle, intermediate, and long cycle. And these are just numbers that were arbitrarily put together. But certain things you can do, like stockpiling, happens on a very quick time frame. Financial hedges, fast product cycles like consumer electronics. So iPhones come out on an annual basis. So those short cycle effects are things that can move very, very quickly. If you're in a place of the supply chain where you've got intermediate cycle effects, where you're looking to build a facility, you're looking to requalify a technology that might be regulated in some way, you're looking to reconfigure supply chains. That can take you time. And then there are other things like opening a mine that takes you a whole lot longer. And so the trick is understanding these different life cycles and what happens, because if you're trying to address a short cycle effect with a long cycle response, you can really get yourself in trouble in a lot of different ways. And I think there's a lot of room to unpack and to think about what's actually happening in each of these spaces, particularly with respect to specific material supply chains, but also across all of the dynamics. Other things that are worth noting is just, again, to think about uncertainty, is that people love having crystal balls and they love very confident predictions, but oftentimes they're not very accurate. Just because there's a lot of uncertainty that's difficult to model, it's difficult to capture. So I think as we look at criticality, there's also room, especially in the context of dynamics, for a degree of humility, saying, look, here's our best guess based on this information. How do we then begin to qualify that in a way that policymakers, decision makers in business, people that are funding research and deciding on projects, have the capacity to understand the relative risks that they're taking on by making choices based on a projection at a certain point in time. And so I think there's room there for some work to be done. So third piece gets at policy. And so geopolitics historically is something that's tricky. It's something that can really shift the market dynamics independent of the underlying technical factors. And so what you see here are, again, I think for this audience, things are relatively well known: the IIJA and the IRA's incentives around critical materials. There is also work out of the EU with their recent Critical Raw Materials Act with certain targets, as well as coordinating work across the bloc to understand how to begin to reshore, friendshore, or otherwise reduce their risk of exposure to different materials on their sets. And then the Chinese side, I think, is also quite interesting, because China is often considered the counterparty to the EU and the US in some of these adversarial critical materials conversations. But China itself also is somewhat progressive in terms of the way it thinks about critical materials. And so what I have here listed are just some key phrases pulled out of the 5-year plan, which is their blueprint for industrial development, that highlights some of the different things that are being looked at here. So I think there's room to begin to unpack and understand and think about these things. But the reason I point this out is that none of these policy choices are made in a vacuum, that there's back and forth between each of these different regions. And if that's something that's of interest, we can certainly talk about that during the Q&A. So where can we go? What can we do to try to take something that is not something that's deterministic, that can be understood in technical terms? How do we begin to incorporate policy factors into our thinking about critical materials risk? So one example actually comes from a report that was written by Matt Zielinowski, who did a lot of work with the DoD, and now he's an independent consultant. But he put out a really nice report in the past month on cobalt supply chains and resilience there. So if you do have time to take a look at that, I think it's well worth taking some time if you're interested in this space to understand the historical context. So Matt asks the question, cobalt, is it something that, we just were surprised by and this is the first time around? Or in the past, when we dealt with it, we just weren't paying attention to the lessons learned and we forgot them? It's actually quite a neat historical unpacking of what were the lessons learned? Why do we find ourselves in the same place with respect to cobalt challenges again? versus past cycles, and what's different and what's the same. Within that report, he actually presents an interesting figure that talks about the cobalt supply chain. And in this case, I'm showing you the distribution first in terms of national distribution. So you see the DRC is really the driver of cobalt in terms of just pure supply quantity. But then he goes further and unpacks and says, in the DRC, there are different companies that actually mine cobalt. Who controls those? And so he shows here, the problem is, if you're in from the US perspective, is that Chinese companies work in the DRC, and that control actually is one of the challenges that requires thinking about if you're worrying about geopolitical risk. So when you think about metrics for political risk, you may say concentration is a factor, and the DRC is one. But digging one level deeper and saying, I have multinational corporations, I have companies that are playing across boundaries, thinking through metrics such as actual corporate control can be much more representative of the political risk than just a national level indicator. The other thing to think about also is that traditionally, a lot of, at least in my experience, the folks that have been thinking about criticality assessments have been in the academic and the government and the nonprofit world. There's a larger ecosystem at play. There are individual companies that have supply chains, that also there are policymakers. And so the ecosystem here involves people that put money to work in financing things. There are regulators, there are advocacy groups. And then within each individual company, there are different organizations of differing size and capacity that are also thinking hard about this question. So I think there's some room for the academic community, especially, to talk to the private sector, supply chain management folks, to understand, what's known, what's not known. And there's some room for some pretty interesting collaboration that can be understood. And then those things can inform thoughts around policy interventions and so forth in terms of driving some clarity there. Last thing I'd like to unpack, and I'm trying to get through this relatively quickly to leave time for discussion, is in the past couple of years, we've seen AI really introduce a tremendous amount of capabilities. So how does this help? We've talked about data and access being a challenge. Well, AI to the rescue. And so what I want to end on is just a couple different things that I've seen over the past couple months that I think are worth just flagging for this audience, just to say there are some really neat capabilities that are being developed. And the trick, I think, will be combining the communities, people that understand AI deeply, with people that understand critical materials, and having that crosstalk. Just having someone that understands AI by itself and treating critical materials as a black box or another search term. Personally, I think that's not the right way, quite the right way to go. But if you have domain expertise in both those areas, I think there's room to really generate some pretty interesting capabilities and results. So I'd like to just show you 3 examples of that and then wrap up. So the first one comes from DARA. This is the German equivalent of the USGS. And what they did is a big data study. So this was, I believe, in September 2022 is when it was published. So they basically did a web crawler and said, if I'm looking for critical material supply chain risk, I can just scrape the web and look for indicators of protests or indicators of public announcements from companies that are looking to play in that space. So this was a meta-analysis that they did a few years ago before ChatGPT 4. But they went through and they found some interesting correlations that they said, well, I can use natural language programming to assist me in my data collection. And now that you have LLMs and the capabilities of the different tools that we have now, you can certainly take this and take this in a much, much stronger direction. The other side of the panel here includes a work from the DARPA working with the USGS, saying, can we apply AI to understand geological formations and where different regions might be more keen to produce mineral supplies or not? So there's a really neat set of work there looking at AI-based analytics, again, combining domain expertise with some of these new tools that are available specifically for materials supply development in this case. Secure data sharing, this is an example from the EU where legislation was passed around a battery passport to try to understand for batteries that exist and operated in the EU, where are they coming from, where are the materials that make them come from, where are they going in terms of at the end of life, is there a recycle use, and to really have this passport that tracks the materials and the carbon footprint and other elements across the life cycle of the battery. And so as you hand off the battery to different owners, the chain of custody is updated within a battery passport. And so there are different ways to think about how do I maintain that passport. And so blockchain and other types of cryptographic tools are being looked at as the mechanism to do that. And the reason is that if you think about handoffs there's information that is valuable, and sometimes people want to share that, sometimes they don't. So finding this balance between sharing information in a way that's compliant with regulatory factors, while also recognizing the proprietary interests of the people that own that data and protecting those in some way, is an interesting back and forth that I think thinking through things like blockchain, differential privacy, a variety of other things that are coming up on the radar of these analytical data sets is one that really can be fruitful in the next couple of years in thinking about critical material space. This last one came to my attention actually as a result of the election in the US. And so this study was interesting, or a set of studies saying, can I begin to do better about predicting election outcomes by using agent-based modeling? But for my individual agents, instead of having them as very simplistic programmed heuristics, let me now have LLMs act as if they were agents and then talk to each other and see if I can aggregate interesting data. So that was used, in, at least the first time I saw it, was in trying to think about, can we be better at predicting the outcomes of elections? But you can imagine adapting tools like this to thinking about critical supply chains. If I can configure an LLM to act like different links and nodes in the supply chain, can I really come up with higher level agent-based modeling results that might be insightful in meaningful ways? So I don't know the answer to that, but this did catch my attention, and that's one I wanted to put out on the table to at least stimulate some thinking. So I've gone through things really, really quickly, but my hope is to have at least opened your mind to think about certain challenges in a way that's a little bit deeper. My sense is these challenges are ones that are fairly obvious once you think about them, and it's easy to recognize. But the question really becomes, how do we do better? And so that's the open question that we left in the perspective, is to say we have some ideas, we see some cool things that are being pursued, but the next couple of years, next decade or more, will be really, really interesting as you look at the research community, try to dig into this, working with private industry, working with governments to really try to help strengthen supply chains and move things forward in that respect. So again, thank you for your attention. I'm looking forward to the discussion on the Q&A, and I think that's it.
I want to thank you so much again, Anthony, for doing such a great presentation and really kind of opening up our eyes to a lot of these risks for critical materials supply, and almost historical. And you went through every segment. So we appreciated that. We also appreciated some of the promising directions and that thinking, especially with this body of CMI here that we have online today. And I would like to open this up to questions. We do have a couple already queued in by Linda, if you want to go ahead and answer those. While he is answering those questions, I just encourage the rest of the audience to post your questions.
Yeah, so Linda's first question is can you have the slides? And the short answer is absolutely. I guess CMI will provide those, but if you need to, you can reach out to me directly. It's good to see you, Linda, again. The red here, if I just pull up the chart on this one, I think that is manganese, according to no, that's not manganese. That's actually, let me go dig that up. Actually, I'm not sure what that is. I might have cut off that part of the legend.
And while we're waiting for a couple of other questions, wanted to know also, Anthony, is there anything specific that you're working on, you want to encourage CMI to work with you on, or?
So I think for me, it's critical materials is a space I've been involved in personally for about 15 years. Right now, I've got personal interests that are actually heading in some other directions related to clean energy. So certainly, I do work with people and thinking about supply chain risk. And this particular presentation was inspired from just at a conference. I was sitting together at a meal with some people, and we just started talking about this. So this is the genesis of these were just observations people made and said, hey, these are challenges that we're seeing. What can be done about this? Instead of just doing the same types of studies and incremental improvements, are there really big questions that need to be dealt with to really improve the fidelity, the accuracy of thinking about risk in a way that can really move the needle above and beyond what we already have? So that's certainly something that, again, is I'm always interested to talk with people about that. The last piece that I ended on, the digital elements, is something also that I find personally really interesting, is that there's a lot of really great stuff moving, and it's moving very, very fast. So there's a lot of capabilities out there that I think people aren't sure what to do with. So finding ways to connect these tools, LLMs or agent-based modeling or other things, to the specific issues that are being faced, the pain points within the supply chain at the level of research or corporates or government. I think there's a real opportunity there to engage in those. So if people are interested in that, I'd certainly welcome the chance to talk more.
Looks like we have 2 more questions queued up already.
Yep. Here we have Jeff
Oh,
Koch.
3.
Says, do you have any thoughts about how to protect domestic industries if they make investments to restart U.S. capabilities so the Chinese don't undercut the price to drive competition out? I think that is the biggest challenge. I mean, personally, I look at it and say the market is one that can be pretty brutal. So this idea of investments, I think with the IRA, you did see a significant push to reshore a lot of things in the U.S. I'm personally not a fan of saying you have to basically build an entire supply chain and within your entire space. I think you have to have a degree of control and access. So domestic industries, I think, at the level of individual companies, that will be tough unless the U.S. has these industrial policies. So tariffs may be something that I think are worth thinking about. But again, the fact that China has industrial policy that's focused in a specific direction means that you need to level the playing field. So I think maybe that's, I'm thinking out loud here. I think that's the main thing is you want to be thinking about policies to level the playing field in order to protect U.S. Domestic capabilities. It's one that I think is politically sensitive, so I'm just trying to think through how to address it in a way that is proper on something that we posted publicly. But maybe that's something we can talk about later on offline. Tom Lagrasso says, with respect to substitutes, the example about LEDs is poignant. Generally thinking about element for element, material for material, technology for technology is effective. Was the LED penetration coincidental to the rare earth crisis? So in that case, I think they actually were separate things that happened. So the rare earth crisis did not drive the adoption of LEDs. In the lighting space, there was a progression from incandescents, which are, basically 90% of the energy that goes in ends up as heat, 10% comes out as light. That was sort of the Thomas Edison, the tungsten wire. The progression after that was the fluorescent bulb with the phosphors, the red europium phosphors, the blue terbium and green terbium, or sorry, the green terbium and the blue europium. That was a significant step up in terms of pure energy efficiency for CFLs and fluorescent bulbs. And then the LED was a solid state technology advance. And what they really needed there was the blue and then the red phosphor, which I think Bill Cohen may be on the line, and he played a key role in that. But the technology development of LEDs and lighting was just trying to get more and more efficient over time. And so the material sets that enabled that just happened to coincide with the time that a rare earth crisis popped up. So I don't think that they were correlated strongly. I think there were some ancillary benefits, but I think it was correlation, not causation there. Bruce Moyer is asking a question about tariffs on rare earth and imports of critical materials. Again, I think this is one where it's a much larger conversation. So I may just opt to kind of defer on this one. And if there's a separate offline conversation, I can offer an opinion on that. Herman Levitt asks, do you account for reserve potential in the risk analysis? So if we go back to some of the traditional methods here, each of these methods, when they were originally developed, let's say in the 2000s and 2010s, the supply risk is divided into a number of different factors, contributing factors, and then your supply risk is basically the sum of the contributions for each of those. So in a lot of these methodologies, one of the concerns is, reserve potential. So if a country has a lot of reserves or has friendly reserves available, that's a positive. If a country does not, that's considered a negative factor. So that'll impact part of the score. So I believe that is something that is considered in most of the methodologies that I'm aware of. And then Oliver Gottfried asks, what is your perception on the potential applications of physics-informed neural networks in this area? I think there's a lot of potential, but I think it requires actually taking a look and seeing what happens. So physics-informed in this case may be partly the physics of the supply chain, so the actual physics of separation. So for example, if I'm thinking about a rare earth material set and I want to use neural networks to develop ways to optimize the separation stages in a liquid extraction, I think there's room for those as the low-hanging fruit. If I want to think about strategically around value of neural networks or modeling strategic risk across an overall system. There, I think you start to run into problems with having enough training data to really begin to move the needle. So I think that data exists. The problem is that companies that exist in a marketplace, they know what they have and they know what they need and they know how much they pay for it. But if you want to start to aggregate that information, that's considered proprietary information. It's competitive advantage for companies. So I think there is a disincentive to share that. So how do you begin to overcome this idea of you have different data sets that exist, but they're just not shareable in a way that's meaningful? Maybe you can anonymize that data and train a neural net on that or something else on that in a way that it's able to pull out aggregate properties. But I'm not sure exactly how that would work. I'd love to chat with people if they're interested in those types of questions and investigations.
We do have a little bit of time for an additional question or two. And while we're waiting, I wanted to ask, just based on the types of questions that we had here, if there was anything else that you'd like to add as kind of an exclamation point.
I mean, I think certainly, the two questions, quite frankly, I kind of dodged around tariffs and domestic policy. I think they're really important ones. And it's hard, I think, I know there's a lot of people that have a lot of different opinions on those. And so I want to shy away from offering a firm opinion saying we should do it a certain way. I think the challenge is that there are within critical material spaces a lot of nonlinearities. So for example, if I look at a lot of the projections that you have about here's where the world will be 10 years from now, 20 years from now, you have models that I think are quite good, and a lot of people put a lot of good work into them. But if you go into the assumptions that underlie these, you have to make an assumption about, what's the trajectory, what's the trend. And so in the case of, let's say, clean energy, if you go back to the IEA's assumptions, that's usually what a lot of people who do studies will say, well, I go back to the IEA and they publish this projection and a forecast of what things will be like. And so from there, that's my foundation from which I now run through all the different other assumptions I stack on, and I can get predictions and estimates about risk and so forth. But if I go back to the IEA and say, where did they get their numbers from? You can begin to find interesting cases where I think there are assumptions that are made that are actually quite simplistic, and they did it because that was the best that they could do. So when I go back, and the reason I tie this back to this issue of complexity and tariffs and other things is the world is really complex, and you see these dynamics play out in ways that are, I think, maybe impossible to predict. So I'm not saying you should try to understand and have a full crystal ball for where things are going, but I think what you want to try to do is to identify the big factors so you're not making huge unforced errors that can be anticipated and understood in your decision-making process. So that's my way of kind of qualifying that piece. So with respect to tariffs, certainly you want to think about industrial policies from China and other places that will tilt the playing field unfairly. You can begin to directly address those, and then you have to start running down this rabbit hole of, okay, well, what is the counter move, and then how do I begin to work these things out? And fundamentally, if I think about investment in domestic industries in the U.S., that's a real challenge, because if I am putting down a capital investment, I need to have some degree of certainty if I'm a bank or another investor that the policy durability or that the markets will be there long enough to recoup my investment. So if I have changes on the cycle of 2 years, 4 years, a political cycle or whatnot, that's something that's really difficult. So there may be ways to find bipartisan ways to get durability in a cycle that allows you to be able to mobilize private capital in a way that's efficient, without necessarily using a tariff as the only tool that's available to you.
Well, I'd like to thank you again, Dr. Ku, for an excellent presentation. You certainly have the audience on today who thinks about the risks and supply daily in their own research areas. So this was very timely, and thank you again for that. And it looks like we did have one jump up from Junqui.
Okay, let me pull up that. Yep. So Junqui was able to clarify that the red colored bar that Linda was asking about is copper. So yeah, I think that's helpful.
Okay. Well, I think this is perfect timing here. as people needing to get to different meetings, so on and so forth. Want to again thank you very much for really providing a lot of food for fodder here. And I know that there are going to be people getting a hold of you. Thank you again for also making available your slides, and you can request those even in the final survey, and we can make those available to you. So I'd like to get off to the last slide where we will have you thinking about what we've got for the webinar, this next session. So again, thank you. Knowing that this particular webinar is going to be available next week at aimslab.gov and also on our YouTube channel. The next webinar in this series is going to be available on January 28th, and we've got Clifford Crown presenting there. Science, engineering, and manufacturing aspects of red box flow batteries. So detail always to be found in the critical times. We hope that this audience here will join us again on that January 28th date. Please don't hesitate to, again, give us some feedback on this presentation in the survey ending, as well as future topics that you'd like to hear about. So thank you, everybody, and we'll see you next in another month.